Okay, everybody, it's week 12, and we're in the website right now. I know we did a little bit on fibers last week. We talked a little bit about stress and strain, and I also emphasized how cool it is that when you multiply stress, which is force per unit area, by strain, which is the change in length over the original length, that you get energy density. So we did that last week a little bit with fibers. Let's see what else is out here on the forum. 5 unread posts. Okay, so Doty. Whoa, look at that. Here are 2 interesting articles about the idea of turning atmospheric CO2 into graphene. Both the articles state that while the process of making graphene does in fact absorb some of the atmospheric CO2, it is not enough to stop climate change from occurring. Okay, well, every little bit helps. I could not find any good links about the actual process, though it is very interesting that it is possible. Well, we'll see. I'll see it when I believe it. I've got my own idea, but it's well, not a little, it's very technically challenging. Graphene can be used in many different applications. Graphene nanotubes, supercapacitors, yep, that's a really good one. So we talked about that sp2 bond last week, so that was, yeah, good one. Graphene, so there's the supercapacitor portion. Graphene nanotubes would be such a great option for building capacitors because graphene has such a large surface area, right? 1 gram of graphene has 19,000 square meters of surface area. Wow, impressive. Which is 10 times the surface area of activated carbon. Yeah, I think the deal there is with the graphene, you have all these just atomic layer sheets giving you all the surface area where amorphous or activated carbon, the bonds are just, they're different. They're usually saturated bonds. This would be a fascinating industry to be involved in. The possibilities are limitless once the hurdle of making this is crossed. I like it. I'm going to take a quick look here. I'm glad you dug that out. Nano energy, the chemical reactions develop. So they're using just a chemical rather than an enzyme. It's ordered atomic surface area. Oh, 1900, not 19,000. Oh well. I think didn't Sean have 19,000? Anyway, it's still impressive. So it hasn't been out that long. Let me see. I don't see a link to the paper. That's fine. We have other things to cover, so I'm just going to move on. And here's the other one. Sorry about the distracting video over there. That's no good. Jeez, man. It's just silly to deal with this. So, here, can I just kill that? Bad choices. It's like, this is what happens when you're inappropriate. There we go. Mid-40s man, they think that's what you need. Okay, so we can turn CO2. Proved it's possible. Sucking CO2 directly from the air can be a trickier process. So the flue gases, because it's there, right? Okay. Mhm. Yeah, where you've already got a high concentration. So it can be better. Okay, new research from George Washington University. Directly capture a few volts of solar and solar heat. Nice. This is smaller than microscope. Yeah. Okay. It's cheaper. That's cool. I like it. Well, every little bit helps. Okay, so again, I don't see the full article, and we won't dive into it, but thanks for doing that research there, Sean Doughty. I appreciate it. All we need to do is go out to the Mansfield Library and find it, so, okay. Here's from Jason. Carbon upcycling technologies. Previously, JRE Petroleum has developed technology, graphite. Oh, cool. Small and easily. Carbon upcycling, graphene, algebra of carbon, nice to accomplish. Is this the link to it right here?
I think that's the website.
Yeah, I'm gonna check it out. You know, it could be, it sounds like those other two sources were academic, and maybe this one is private.
Yeah, it seems more used kind of
Well, I think what they're leaving out has developed a patented proprietary technology. Is the issue there? Okay, so you just pasted what was in there already?
Pretty much.
Yeah. Okay. Nice. And who are these guys? CCEMC? What's CCEMC, do you know?
climate change and emission something.
Are you trying to read it at the very?
On the tab, it says climate change and emission.
Oh, okay. I think it's probably here too. Climate Change and Emissions Management Corporation, okay. Maybe they are Canadian, huh? Just missed our deadline, oh well. Hope somebody comes up with something cool. Well, it's neat that they're running those other processes are being run with solar PV and solar thermal, because, one issue we ran into making hydrogen is we had to turn on this giant electrolyzer, and the majority of that, we didn't have any control over where the electricity was coming from, and, burning coal to make hydrogen was kind of yeah. So, the holy grail there is to get all of your energy from a clean, carbon-free source. Okay, those are good. What else? I thought I saw 4 unread. There's 2 replies. Weak discussion, natural fibers. Oh, and maybe nobody responded to my, Doty responded to hemp industry, okay. Tensile strength. What's that?
I think it's the same one I posted.
Oh, okay. The Natural Society.
Society,
Yeah.
yeah. They have a lot of cool information.
So So better tensile strength, better tear strength. I'm guessing when he says tear, this must mean a shear force. So tensile means you're pulling something apart like this, and I'm thinking, I've never heard the word tear strength, but it probably just means you're pulling it apart like this. You're shearing it apart rather than pulling it directly apart. And this is another thing I want to say for the record. It's incorrect to say 266 pounds of pressure. Pounds measure force, and pascals measure pressure. So you hear that a lot, but the correct engineering terms on this would be to say 266 pounds of force, because pounds measure force, whereas pascals or pounds per square inch measure pressure. There we go. Yeah.
Pressure is more of a compression.
No, so the question is whether pressure is compression or not, and I can give you a pretty quick overview of that. It's actually kind of fun. If you guys ever consider taking the pre-engineering here, you'll see something like this. So last week, what I started off with was just a cylinder, and you had an area here. It was being pulled with some force. It had some initial length, and it was going to be displaced by some value x. And so we have that stress equals force over area. We have strain equals displacement over length. And I showed you, so this is the notes from last week, I'm just quickly doing it, that as you pull something, here's strain, here's stress, pop, and then it breaks. All of this is basically the work to failure, or also energy to failure. Energy and work are the same thing. So the question was, isn't pressure just compression? Well, the answer is no, and I'll show you why. So if you have a chunk of matter, and typically we'll think of this being a chunk of solid matter, but this could be a chunk of air, it could be a chunk of liquid, doesn't really matter. This is the x direction, this is the y direction, and this is the z direction. Now, I can push on this thing. I'm just going to call this fx, fx, but I can also pull on it. So I'll just draw double arrows. I can push it or pull it. So if I'm pushing, it's compression. If I'm pulling, it's tension. And then same thing with y. I can do this, push or pull in y, and I can do the same thing, push or pull in z. Now, when I do that, what I end up with is something that looks like this. So if I'm going to write it, and I wrote stress before. Remember how I wrote stress equals force over area? Well, if I'm pushing or pulling on the F side or the X side, I can say that sigma xx equals Fx over Ax. So this is the force on the X side. That's the area of the X side. And the reason I drew two X's is because you can also, on the side of the material, you can go Fy, and you can do Fz. Well, what's that? Well, I've got here's my chunk of material, and let's just do it this way. So here's the X side. I can push on it in this direction. That's a normal force. But these last two arrows, Fy or Fz, those are shear forces. So the friction forces. But friction forces obviously can pull something apart. So what you end up with along this matrix, and this is, if you've done algebra, you've probably done a little bit of matrices, but you can have sigma xx, this is kind of new information, sigma y, y, sigma zz, and those are the normal stresses. But if you're pushing on the x face in the y direction, then you have this thing of sigma xy, sigma xz. So that's basically the result of that one that I just did and that one that I just did, those other two forces. And then you can see that you can easily round that out and have sigma yz, sigma yx, sigma zx, and sigma zy. And really, all that is, if this is our chunk of material, bring this up a little bit. This is our chunk of material. You can see it's got again, the x face, the y face, and the z face, and I can push or pull normally. So this would be called compressive stress, and I can also pull it, and that's tensile stress. But if I shear it like this, that's shear stress. So therefore you have 6 sides to this thing, and on each side you have normal, shear, shear. You also have shear, normal, shear, and then you have shear, shear, normal. And so, this top row represents all 3 ways you can load the front and back sides. So kind of a long-winded answer, but stress has the same dimensions as pressure. And again, pressure can be positive or negative. You can pull a vacuum. The weirder thing, and this is something that I was trying to explain to my son a little bit over spring break as we were talking, and this actually has a lot to do with bioenergy. The fact that in a tree, you can have the suction pressure of capillary action that pulls water up the roots. We all know that if we were to suck all of the air out of a vessel, that the lowest pressure you could get would be absolute zero. You can't really have a negative pressure, and I think that's where your thinking is coming from in terms of dealing with gases. The weird thing, though, about trees, which are sort of solid liquid interface, the lignin tubes themselves are solid, the water is liquid, you can actually have negative pressures that are two orders of magnitude smaller than absolute zero. So you actually can have a negative pressure inside a tree. It's kind of cool. Yeah, because think about it this way. And this is getting back to that the carbon nanotube thing. If I'm pulling the negative pressure in here, the tensile force, the tensile pressure can be a lot less than zero, because you have to push the other way to put it back, and that pressure can be way less than absolute zero. It's kind of like, is it really less than zero? Well, yeah, it really is. Other things like temperature, it's hard to think of like negative temperatures or negative masses or negative energies, but pressure is one of those things that can truly be negative. So, okay, I think that wraps up fibers. And I even got to do a little bit of mechanics and materials discussion. Thank you, that was good. 244. Yeah, so that wraps up week 12, which is where we are. Kearns has week 15 out there. So there's really just, I'm looking back at my calendar, and we are in we're technically in week 12. Because next week is 13, this is week 12. So there's really only 2 weeks left after this, and I think Kearns had week 15 as review. So there are not 16 weeks in the semester. So I'm glad we're getting into week 13 now.
Are we gonna have like any type of final rate?
Yeah, let's take a look.
I didn't see.
Yeah, here's the final. I'll go ahead and just let that guy be shown. Yeah. And I'm gonna open up the final, just on Monday of finals week, and just let it roll as long as you guys need it to, so. Yeah, there's the final. Yeah. The end is in sight. Okay, environmental impacts. Let's just take a look at this. Actually, I'm gonna pause the recorder and I'll get back in one quick sec.